Hello, welcome to the online lecture series of fluid mechanics. So already we have seen the derivation for flow through pipe, that is Hagen Poiseuille flow, and from this we got the various equations for velocity distribution as minus dabba p by dabba x into 1 upon 4 mu in bracket small r square minus r square, the maximum velocity equation u max as dabba p by dabba x into capital R square upon 4 mu. The average velocity u average is equal to dabba p by dabba x into r square upon 8 mu. The discharge equation, that is dabba p by dabba x into pi r fourth upon 8 mu. Shear stress distribution tau is equal to dabba p by dabba x into small r by 2. Maximum shear stress equation tau max, that is at wall, it is dabba p by dabba x into capital R by 2. The pressure drop equation, that is HF is equal to 32 mu u average L upon rho g d square, and this may be P1 minus P2 upon rho g, that is HF. Ratio of average velocity to the maximum velocity is half, or you can say u max is equal to twice of u average. Ratio of velocity distribution to the maximum velocity is 1 minus small r square upon capital R square. Now we will see the numerical. The very first numerical is, there is a pipe of zero point 0.2 meter diameter carrying a liquid in laminar region. A pitot tube is placed in a flow at a radial distance of 15 millimeter from the axis of the pipe, indicates velocity of 0.5 meter per second, and we have to calculate maximum velocity, mean velocity, discharge in the pipe. So we will first write the given data. So here the pipe diameter is given, it is 0.2 meter, while from this we can get a radius as 0.1 meter, and there is a pitot tube placed in a pipe which is measuring a velocity at a distance of 15 millimeter from the center. So the radius is 15 millimeter, that is 0.15 meter, while the velocity at this point is 0.5 meter per second, and you have to calculate maximum velocity and mean velocity and discharge in the pipe. So as the velocity is given at a 15 millimeter radius, so and we have to find out the maximum velocity, it is better to use a formula of the ratio of velocity distribution to the u max, that is 1 minus small r square upon capital R square. So we have been given with a small r, that is 0.015, and capital R as zero point 0.1. So this would be u max upon u max, that is 0.9775, and from this putting the value of u as 0.5 meter per second, you will get u max is equal to 0.5115 meter per second. And there is a relationship between average velocity and maximum velocity, where the maximum velocity is twice the average velocity, and hence average velocity would be half of maximum velocity, and it is 0.2557. So we have to calculate discharge to the pipe. We know that from the continuity equation, q is equal to cross sectional area of pipe, that is a into u average. So already we got the u average as 0.2557. So we need to calculate a cross sectional area of pipe is equal to pi by 4 capital D square. After putting the value of D as 0.2 meter, you will get a cross sectional area 0.0314 meter square. Now putting the cross sectional area and the average velocity in the equation of discharge, so after multiplying 0.2557 and 0.0314, you will get a discharge as 0.008 meter cube per second. And if you convert this into liter per second, multiply this by 10 raised to 3, you will get this as 8 liter per second meter cube. And viscosity as 0.15 poise, it's pumped at a rate of 5 liter per second through a 40 centimeter diameter pipe. So here the density is given 800 kg per meter cube, while the viscosity mu is given 0.15 poise, that is 0.015 pascal second, and it is flowing at a rate of 5 liter per second. So converting this liter per second into meter cube per second, so it is 0.005 meter cube per second, and the diameter of pipe is given, it is 40 centimeter, so it is zero point 0.4 meter. So and the pipe length is given, it is 1 kilometer, so converting this 1 kilometer into meters, it is 1000 meter. So we have to verify whether the flow is laminar or not, and the inlet pressure is given, that is P1 400 kilopascal, and along with this we have to calculate the pressure at the end of pipe, that is P2, and the shear stress at the wall. So we know that the discharge is given by cross section area of pipe into average velocity, and we have been given with a discharge and the cross section area of pipe we can calculate by using the diameter of pipe, and it is 0.1257 meter square. So using the discharge and the cross section area of pipe, we, we get the average velocity as 0.0397 meter per second. And now we have to verify whether the flow is laminar or not. So to verify whether the flow is laminar or not, we have a dimensionless number called as Reynolds number. So Reynolds number is nothing but rho u average d upon mu. So we have been given with the density rho, that is 800 kg per meter cube. Average velocity we got 0.0397 meter per second, and the diameter of pipe as zero point 0.4 meter. Along with this, the viscosity of fluid flowing is given, it is 0.015. So after putting all this value, the Reynolds number that we get is 847, and as it is less than 2000, we can call this flow as laminar flow. Now we have to find out the average velocity, not average velocity, we have to find out a pressure gradient using the average velocity, that we need to calculate the pressure at the end of pipe. So average velocity is nothing but dabba p by dabba x into d square upon 32 mu. Initially on the very first slide we have given it as dabba p by dabba x into capital R square upon 8 mu. So instead of this, here the diameter is there. So using this, average velocity is there 0.0397, d is there 0.4 meter, and the viscosity is 0.015 pascal second. So putting all these values, you will get a pressure gradient as 0.1191 pascal per meter. So we know that this pressure gradient over a length may be written as the initial pressure minus final pressure over a length divided by the length of pipe, that is dx, and here in this case length of pipe is 1000 and P1 is given as 400 kilopascal. So converting this 400 kilopascal into pascal, you will get 400 into 10 raised to 3 minus P2 divided by 1000. So from this we can get a value of P2 as 399.88 into 10 raised to 3 pascal, that is 399.88 kilopascal. Now as we got the P2 and the pressure gradient, so it is very easy to find out a shear stress. So for shear stress, the formula is dabba p by dabba x into small r by 2, and we can put the boundary condition to find out a shear stress at the wall. So at the wall it is small r is equal to capital R and tau is equal to tau max, and hence tau max would be dabba p by dabba x into capital R by 2, and after putting the value of dabba p by dabba x as 0.1191 pascal per meter and the radius of pipe as zero point 0.2 meter, so you will get the shear stress as 0.0282. So this is all for this numerical. So similar kind of numericals would be there, and there is a high possibility of numericals on this section because many of the problems in a actual life involves the flow through a pipe. So thank you all.